Okay, it's time to begin Unit 10B, Moments of Inertia. Last time we were talking about the kinematics, what the accelerations were, and now we're moving to dynamics, where those accelerations come from in the first place. Now, the analogy for mass, when you get into the rotating world, we already had, by the way, the analogies for displacement, velocity, and acceleration. You know what those are by now. Now we have to do mass. And that's the moment of inertia. Depends upon how far you are from the axis, and it depends upon how much mass you have, really. And the simplest case is that of a hoop about, well, point mass. Point mass in the axis. We're looking down the axis here, so it's going around just as it would if it was doing simple circular motion, constant speed. And you got the mass, it's a distance r away. Well, it turns out the mass is multiplied by r squared to give the effect of inertia in this rotating scale. This makes sense, kind of, because to get alpha from acceleration, you had to divide by r. You can imagine on the other side, you'll be multiplying by r to get the force, to get the torque. We already actually done that. And so if you think about F equals ma and what you have to do to make that work, the r squared makes perfect sense for this point mass from an axis. So this is the simplest case. If we go back here, you see more complicated cases. And on the left side, mr squared is you have a hoop, it's about the axis going around the center. That is pretty obvious because all the mass is the same distance. When you start looking at the solid cylinder underneath it, it gets a little bit more complicated now because there's mass at different distances. And so we don't expect you to be able to get this. We'll tell you what it is, and here it is, mr squared over 2. And then the sphere becomes 2/5 mr squared, and all these formulae on the left side, and most of them on the right, a couple of exceptions, are for axes that go through the center of mass of the object. And later in this class, I'll tell you what to do when it's not going through the center of the mass of the object. We have one example of that. That's that on the right side, 2 down, we have, I don't really, I guess this pointer may work. I'm not sure if you see it or not. The solid cylinder around its center is, of course, the center of mass, if it's a symmetric rod. But when we go to the one below that, it's a thin rod around the end of it. That is, of course, something quite different and not through the center of mass, because obviously center of mass isn't going to be at the end. And we'll learn how to get from one to the other later on in the class. Okay, so there we have point mass, mr squared. Back to these, you should think about the answer to this one, which, oh, I'm not showing you anything, so I guess you can't do anything here. We'll skip that. And now we get to the Earth, its radius, distance from the sun. What is the moment of inertia of the Earth as it spins on its axis? So when we're doing how it spins on its axis, we have to ask the question of which of those formulas we should use. Well, first, does the Earth spin around its center of mass? And of course, there's the Earth, right? It's a sphere, and it's spinning around here, its axis. Axis sort of chunks in there and comes out the other side. And yes, it is spinning around its center axis. So what is its shape? And its shape is, it's a sphere, right? So we go to the table. And what we find is that for a sphere, sphere is equal to 2/5 mr squared, about the center mass, which is the center of the sphere. We're assuming uniform spheres, and we write this down too, by the way. And so now it's just a matter of plugging in. What's the mass? Well, it's the mass of the Earth. What's the radius? Why, it's the radius of the Earth. This is irrelevant. And you plug in the numbers, and you find that it's equal to this one over here, let's see. So step by step, you need to be able to get moments of inertia of various objects by looking them up in the table, except you should really remember the mr squared for that point mass going around. That's when you really need to know. And the hoop, because it's the same simple thing, you probably should know that too. So here's a slightly different problem. Now we want the moment of inertia of the Earth as it orbits the sun, right? So here's the sun there. And here's a big circular orbit. And the little blue planet going around. So that's Earth. And this radius here is this one. So the radius of the Earth is irrelevant on this one. That's the mass of the Earth. And so what does this look like? Well, we're certainly not going around the center mass of this. In fact, this looks like a point mass. And if you take a point mass, then you're going to get a different I. You get I is equal to simply mr squared. Right, there's mr, there's r, there's m. You plug them in, and you find that it is this one. Note the units of our moment of inertia, kilogram meter squareds. There's no special name for that. It's just kilogram meter squareds. And as we'll see, these things will work out in the end when we get to problems. Okay, let's look at a different question. Put 4 objects at the top: solid ball, solid disc, hollow ball, hoop. And as in most of these problems, if it's not a point mass going around, or sometimes the hoop will tell you what the moments of inertia are. It doesn't hurt to put a few of them on your list, but we'll really tell you what they are. And we want which has the greatest speed at the bottom of the ramp. Now, if they were sliding, which I'll put in a box because they're not. And then we already did this, and they have the same V because they have the same mass. But of course, here they're not sliding. Right, roll without slipping, in fact. So what do we do? Well, now instead of M, we have to look at I. And remember, I is the resistance to rolling faster. Right? M is the inertial resistance at the moment of inertia. Just like inertia, M, inertial mass, made it harder for an object to speed up, moment of inertia makes it harder for it to roll faster. And so the larger the moment of inertia, the slower it starts to roll. And so the greatest speed then is the one with the smallest I. Now, when we get to kinetic energy, you'll actually be able to calculate this differently. But now, what this is aimed at is just this idea of inertia. It's like inertial mass, moment of inertia for the rotation. So which is the smallest here? Well, it's clearly look at the front factors, 2/5, half, 2/3, 1. And so that's the smallest. So that's the one that works. Okay. Now, same problem, except it's run in reverse. So where we start here is same problem, let's say almost, but in reverse. And what does that mean? Okay, it starts with motion. And we're trying to stop it. So the one that's hardest to stop is the one with most inertia. And so we're looking in the other direction, right? The one with a small moment of inertia it's easy to stop. The hoop is the hardest to stop because it took the most work to get it going. And so that one is the hardest to stop. Okay, at this point, I want to remind you of something that was in the lecture. Where's our focus gone? Okay, got us back. I want to remind you of something that was in the lecture, the parallel axis theorem. And so this is what you do when the axis is not through the center of mass. And so let's think of an axis here, and let's put a rod here. And we can look up for this. This case here has the moment of inertia equal to 1/12 ml squared if this thing has the length of L. So the new question is, what if we put an axis right here that's parallel? So in other words, we know rotation around the center of mass. What is rotation about the end? The same rod, right? So this one is through the center of mass, spinning around there. But what about if we spin it around the end here. How does that change the center of mass? And the answer is the parallel axis theorem. So I parallel axis, such as that one, is equal to I center mass plus md squared, where m is the mass of the object and d is the distance between axes, distance of parallel axis from the center mass one. Now, if you look carefully, this is a point mass formula, right? So what we're really doing, sorry about that, and you thought I only did that in class. So what we're really doing here is we're taking a, is the center mass is swinging around the axis as a point mass, a distance d from the axis. So when we move to the end of this rod, rather than to the middle of it, then the center mass is over here. That's swinging around at this distance d away. Okay, so for our particular case here, we can now write down I at the end is equal to I center mass plus m. Okay, the distance between these two now is L over 2 squared. And this part here was equal to 1/12. So 1/12 ml squared plus 1/4 ml squared. You can add those together. 1/12 and 1/4, right? 3/4 is 4/12 is 1/3. ml squared is the I about the end. And if you go look on their formula sheet for a rod about the end that I showed you a few slides back, you back up the video if you want to, you'll find that's what it is about the end. This is the one that was given twice. So be prepared to use this. If you have a sphere, and instead of around the middle of the sphere, you're going around the edge of it for some reason, well, you're going to have to use this. So I want you to be aware of that and able to use it. Okay, next, let's calculate some other moments of inertia. We'll start here with, okay, can't quite see it. There's a beam with a red disc. I used this in a demonstration, I think it was last time we met, maybe the time before. It was last time. So there's that red weight we put in the end, and that's the disc, that's 0.5 kilograms. The mass of the beam is this, length of the beam 1.5 meters. We want to know moment inertia of the beam and the red discs. Right? This has one red disc over here. Right? So I then, of our whole system, is equal to I of the beam plus I of any added discs. And so that's equal to 1/12 mass of the beam, length of the beam squared. Right, this is the length of the beam is this, the mass of the beam is that. And then we have to add, now this is like a point mass out here. So we just add a m of the, I'll just call it red. That's the color they were in the demonstration, and r squared for the red. And so this is equal to m red, and this is equal to R red. And if you just matter of plugging the numbers in right now, you get 0.305 kilogram meter squares. So now we can know the I. If we were given a torque on this thing, which of course you get from this mass, that's its center mass, then we could actually get the angular acceleration, right? So here's a problem for you. I want you to think about this before I tell you the answer, like I usually want you to do. What is the torque here? Well, we draw our free body diagram. We put the rotation axis right where it tells us to, in the middle. We'll put some forces on this, right? There's the weight. Any other forces? No other forces, right? No, nothing on there, just our beam. And so the torque net is torque from the weight, which is equal to W times 0 meters, pulling straight down from the axis, times sine of phi, which is of course 0. And so torque equals 0, torque net equals I alpha, implies alpha equals 0, 2. So it's that. Now this is probably a bit further than you'd have to go in terms of what work you'd have to do to get there, but that's the kind of thing that you will need. Okay, I already did the other side of that one, and let's come up with this one then. What is the net torque of the beam about axis A? Okay, so we can start this the way we would start any of these others. Distance between the pegs is 0.2 meters. So this distance from here to here is 0.2 meters. Down here there's 1, 2, 3, so this is 0.6 meters. Let's call this M1, and this is M3, which is 3 times that, 1.5 kilogram. And how do we do this? Well, you calculate it out in the steps, right? Torque net is equal to torque beam plus torque. Probably should draw a few things in here. W1, W beam, and W3, and plus torque 1 plus torque 3. And the torque of the beam is going to be 0. And that's simply because our beam is equal to 0. It's about the center of mass. Plus weight 1 is M1G, distance 0.6 meters, angle. That's a good one. What's this angle from here? It's this angle here is 90 minus 30, right? So that's 60 degrees. And this angle over here is, let's see, if that's 60, then this is the rest of it. So that would be 180 minus 60, 120 degrees. And next thing we have to think of is this plus sign right? This is trying to pull it down that way, and that's a negative torque. So a bit of a minus here. And the minus sign, I'll just remind you, is because it's trying to go clockwise. That's clockwise. This one is going to be plus, and that's because it's counterclockwise. And it's M3G times 0.2 meters. Now, if we look at this, okay, M3 is 3 times M1, and that's 3 times that. So if we were to factor out G and M1, we'd have minus 0.6 plus 0.6. And so we end up here with a big 0 Newton meters. So I think it's balanced. Oops, no, whoop. Wait a minute. Now, tell me one thing here. What was forgotten and doesn't make a difference? What's forgotten, of course, is that there has to be a sine 120 degrees in here and a sine of 60 degrees in here. Okay, now you tell me if that makes a difference or not. Well, of course, you put in your calculator, you find the sine of 60 and sine of 20 are actually the same. So no, it doesn't make any difference. Now, looks here like we're just calculating the torque. That's something you could have done quite a while ago. Now, where can we move from here? Well, if we wanted to, we could go ahead and calculate the moment of inertia, which would involve the moment of inertia rod about the middle and the masses. It would look a lot like we did, not on this one, but on a lot like on this one, calculating what I was. And then from the torque and from the I, you get the angular acceleration alpha. And from that, you could either just take it as an answer, or we could ask you things about kinematic equations involving that. So there's 2 more things that I want to show you here. This is an acceleration. So let's think about this and get going with it. So this time we're actually asking you for the angular acceleration at the instant shown. And you take a look at this and say, okay, we're given forces, right? Force, angular acceleration. This one says, well, this is Newton's second law. Newton's second law now is torque is equal to I times alpha. And so that's what we're going to be using here. Okay. This is the rake handle. That looks to me like a narrow rod. This is the point, that's the axis. And now we need the moment of inertia of this rod about the end. Handle about end. And that's equal to 1/3 ml squared. How do we know it's 1/3 ml squared? Because we did that sideways, but we still did it. So we have I. We need a torque. Now, you see this thing here? 10 centimeter long, mass is negligible. Okay, so this is going to give us no mass, no I from it. So this is the I total. And so that's going to come into here. That's what we want. We need torque. And clearly torque's going to come from here. So what is the torque? The force is this way. The angle is, well, we could use either this one or the one all the way around. This one will work for us. By the way, is this going to be plus or minus? Let's try and make this spin that way. That way is counterclockwise. It's going to be plus. Now this is 40 degrees here. Then what is this one over here? Well, you got to think about the angle, but think about if this went all the way down close to 0, then that would go up, and this would get smaller too. So it's that, it's not its complements. This is actually 40 degrees in here. And that is our B. So our torque is equal to 520 newtons times the distance, 10 centimeters. Better put that in meters, 0.1 meters, sine of 40 degrees. And that's going to be equal to I alpha. I, we better calculate, I total is equal to 1/3 m. Well, let's put in m. 5 kilograms and 1.4 meters squared. And so let's go ahead and put this into a calculator, which I'll do here for you. Okay, so if we put the numbers in, we end up with 10.22 radians per second squared for being alpha. Because Newton meters, remember, is meters squared, kilograms per second squared, kilogram meters squareds go out, that with 1/2 squareds, and the radians come in for free. Now this one didn't happen to be there, so whoops, made a mistake on that set of choices. And so before we end part 10B, I wanted to do one more thing though, and that is to pull out an old, oh, got that again. Okay, we get the focus, we bring the focus down, there we go. So bring out our old friend, a yo-yo, old butterfly. Now, if this thing is wrapped around in this direction, so it's towards us on the top, and I pull it, then towards me, obviously, then what's going to happen? Oh, it's going to run away on me. So let's see, we've got a red yo-yo, and it's got a shaft in here. And if I pull the string at the top this way, and then I get a torque. That's a little raw of the axis on the inside, and the torque is going to be around this way, and so it should roll. It should go this way and roll to me, right? So this shouldn't surprise anybody. I pull this, and hey, it rolls right to me. Now, what happens if I flip it upside down? Now, torque's on the bottom, right? So I can push this up just to not there. Where I can see it. I draw this. Now we're pulling off here in the bottom, and so the torque corresponding to this should be this way, and that would suggest it should roll away from me. But guess what? It comes to me even faster. What's going on here? It likes to do it over and over again, right? If I pull it this way, it doesn't nearly come that much faster at all. But once you start shortening that thing, it just zooms right across. So what's going on? Come up with anything yet? I hope so. Because remember, there is a surface down here. And that's no slip. I didn't see it sliding anyway. And so if I'm pulling this way, then this is gonna pull that way with an equal magnitude. But this radius here is bigger than that little radius there. So it has a bigger radius. Both, by the way, are 90 degrees. In fact, whenever you get a string and it's pulling on some kind of axle, it's going to be at 90 degrees, because if it wasn't, it unwrapped till it was. Okay, so bigger radius, and what does this mean? This means that the torque from friction, which is what's doing that no slip, it's actually static friction, is greater than the torque from T. And so it actually goes, the this way wins, and it still goes towards me. And the reason why it goes faster is because that's a lot bigger than that distance from the axis. So I actually have a lot more torque. Much more than makes up for this other torque. I wrote blue going the other way, and so with more torque from that larger distance, you get a faster alpha, and it moves faster. So that explains the whole picture for you in nice physics terms, which is the end of lecture 10B. And so that will be it. I will see you next time.